All right, so I want to talk about a concept that's important in Project 2, and it's important anytime you're using a computer, which is the idea of how to use the computer to compute integrals numerically. So in Project 2, you have waveforms that look like sawtooths. So they're actually triangle waves, which is a version of a sawtooth wave. And so I ask you to take a look at how to use the sawtooth command in MATLAB. So Google that. There's some examples that'll help to create the waveform like you have. In this particular case, I've generated a sawtooth waveform that starts at 0. All right, so I see at the beginning of a period, it starts at 0 and it rises to 4 and then it resets back down. And in looking at this, it looks like I've got one period right here, and I can see that I start that period at negative 0.5 times 10 to the minus third. Notice that MATLAB puts that little multiplier down there to make it a little bit easier to read the graph. So it says negative 0.5 times 10 to the minus third is where I start a period, and 0.5 times 10 to the minus third is where I end it. So in this case, it looks like t over 2 is at 0.5 times 10 to the minus third, and negative t over 2 is at negative 0.5 times 10 to the minus third, meaning that a period is 1 times 10 to the minus third, and these are all in seconds. So that would be 1 millisecond, which if I wanted to talk about my fundamental frequency in hertz, that would be 1 over t, or 1,000 hertz, or a kilohertz. And my omega naught would be some kind of a nasty number, 2 pi over t. So 2 pi times 1,000. And I don't want to calculate that as a number because it would be ugly. Okay? All right. So when we talk about the idea of performing numeric integration, all right, what we're trying to do is to calculate the area under the curve. So as an example, let's say we wanted to calculate the average value of that waveform. Well, we know the average value is always alpha 0, the zero order term in the Fourier series. And that is, by definition, the average of the waveform, which is 1 over the period times the integral over a period. In this case, let's say my integral over a period, I'm going to start it at negative t over 2. I'm going to go to t over 2. And it's the integral x of t dt. Now, that area, all right, this is 1 over t times the area under the curve. So the area under the curve is just simply this area that I'm hatching out right here, right? That's the area I need to compute. All right, now that happens to be a triangle, so that's pretty easy to do, right? So it's 1 over t times, for the triangle, 1/2 the base times the height. So what's the base of this triangle? Well, it runs from here to here, right? That's one period, so it's t. All right, and the height of this guy is 4. All right, so 1/2 base times height. So the t's cancel, and I end up by saying this guy has an average value of 2. Now that obviously is a very simple thing to do, all right? But let's say I wanted the computer to compute that for me. Well, to do that, I can go back to things that we learned in calculus, right? So in calculus, what you said is, well, if I look at a curve, right, I can break up that curve into little boxes underneath of it, and I can basically compute the area of each of these boxes. And I can make them boxes, or I can make them trapezoids. And a trapezoid, you learned, was a better way to approximate. And we talk about what's called the trapezoid rule. So I can go through and using the definitions that are given in this graph, I can relate that to this numeric value here. And obviously, if we allow these boxes or these trapezoids to get very, very thin, infinitesimally thin, I get the true integral. The wider those boxes are, the wider those trapezoids are, the worse the error is. Now, you don't need to go back and remember all the details specifically of how the trapezoid rule works. In MATLAB, we're able to use a command called trapz, which performs the trapezoidal rule. If you want to learn how to perform that, you can go to Google that. You can basically Google MATLAB trapezoid Z, and you will learn a little bit more about how that command works. Now, I'm going to give you a couple of examples of that are very similar to what's used in problem 1 on project 2. So let's say I wanted to compute that area, all right, underneath of the curve from there to there, from negative 0.5 times 10 to the third to 0.5 times 10 to the minus third. okay? So in this case, what I do is I defined a time vector that begins at negative t over 2, ends at t over 2, and in this case, I chose steps of t over 10,000, okay? And then I created the x vector. So this is my x of t. I created my x over that period. So to see how I came up with this particular functionality right here, you need to go and look at the MATLAB help page for the sawtooth command. And specifically, I would go to Google and I would type in MATLAB sawtooth, and there's a number of good examples. You'll need to look at the examples, and you'll probably need to think a little bit about the description of this thing. All right. Important thing to remember is that all the MATLAB periodic functions like sine, cosine, square, sawtooth are defined in radians. All periodic functions are defined in radians by definition. All right, so you need to probably think about that a little bit. But notice what I did. Okay, I called this command trapz, which says I want to integrate the integrand I called int. So in this case, my integrand, the thing that I'm integrating is just simply x. I loaded x into my integrand. And I said, integrate this integrand at the times outlined in the t vector, and then multiply that by 1 over t, because ultimately, just if you remember what I'm trying to do is I'm trying to say alpha 0 equals 1 over t times the integral negative t over 2 to t over 2 x of t dt, okay? So this piece right here is performing the integral, and then I need to multiply that by 1 over t because that's part of the definition. Now, if I look at what that is, I guess I didn't include that here in my slides, but it works out to be about 1.998, or maybe it's I'm not sure how many nines are there. It might be 1.998, very close to 2. There's going to be some error because, again, this is numeric. There's some approximation that's going on here. All right, so it's close to that, okay? Now, in the project, what I ask you to do is to use this same numeric approach to calculate the Fourier series coefficients, right? So again, alpha 0 is pretty easy to do, but if I'm talking about the first harmonic or the second harmonic or the third harmonic, it gets a little bit tricky. All right, so let's say I'm trying to do the first harmonic. So remind ourselves that when I'm talking about the first harmonic, I'm talking about C1 cosine omega naught t plus theta 1, which we know is always alpha 1 e to the j omega naught t plus alpha minus 1 e to the negative j omega naught t, like so, okay? So I need to calculate the alpha 1 and the alpha minus 1. And we remember that alpha n in general is 1 over t times the integral over a period. It can be any period, but I'm going to keep it at negative t over 2 to t over 2 x of t times e to the negative j n omega naught t dt, okay? So notice what I did here, all right? Here's where I'm computing alpha 1, and here's where I'm computing alpha minus 1, so I called it alpha m1, okay? So this is alpha 1, and this is alpha minus 1 down here. Notice what I did. I did x dot multiply exponential negative j times 2 pi over t, right? 2 pi over t, this guy here is my omega naught. My n value is 1, right? And then I have the t vector in there. Now notice I did the dot multiply because I want to take every entry in x and multiply it by the corresponding entry in that exponential vector. Okay, and then what I did was I took 1 over t times that integral, right? So I made my integrand in this case this guy, right? X of t times this exponential function. And I did the dot multiply because remember, I need to multiply each individual entry in x by the corresponding entry in the exponential function, okay? All right, so that gave me my alpha 1. And then I do the same thing for alpha minus 1. The only thing that changed here is in my exponential function, I made that a minus 1, okay? So I do that, and then to check myself, what I did was I said, well, remember, our definition here for x of t is that if I know the alpha n values, it's supposed to be the case that I can go from negative infinity to infinity alpha n e to the j n omega naught t, like so. Okay. Now, in this case, I'm approximating this. What I'm doing this is I have my alpha 0 plus I have my alpha 1 e to the j omega naught t plus my alpha minus 1 e to the negative j omega naught t. In other words, I'm plotting only the DC term and these two guys together, giving me the first harmonic. Okay, so that's what I've done here. And so here's my, and I just did this over one period. So this equation, I called it x approximate because it's not really x, right? I showed my little approximately equal to here because I only included the DC term and then two components that give me the fundamental. So I included one harmonic and the DC term. Okay. All right. So I called that x approximate for that reason. And you can see here how this equation down here, which I wrote in MATLAB, matches the equation that I wrote up top from the math. Okay. All right. Now notice what I did here, right, is I then plotted it. So what I see is basically my red waveform is my first harmonic plus my DC term. So I can see that the average value 2 appears to be here. And I can see that the fundamental appears to be here. Okay. Now that I know that I'm right, and the way that I sort of checked to make sure that my answer was right was I just added more harmonics, right? So I basically did a for loop to do more integrals for me, right? All using the trap z function. When I did that, in this case, what I did was I said, well, let me do x approximate. Let me have n go from -10 to 10. So in this case, I'm including the DC term and the first 10 harmonics. All right, the first 10 harmonics. And when I include the DC term in the first 10 harmonics, I say that's approximately equal to alpha. And I can see that it's approximately equal to x, right? And it's getting pretty close. I can see that the red waveform now is tracking pretty closely. And again, yeah, there's a little bit of variation here at the edge, but it's not too bad. The other thing to remember here, this may look a little bit strange where this guy's diverging, but remember I don't have the full period here shown out. Remember the original waveform was going up and going like that, right? And then it would be doing the same thing here. So the fact that this guy is starting to rise up here, the approximation makes sense, okay? All right, so the important thing for you to take away from this is how to use that trap z function to be able to compute those numeric integrals. You're going to need to do that a couple of points throughout this project.